Next, we'll talk about a maximum flow problem. These type of problems arise frequently in supply chains where we need to assess our capability to deliver a certain commodity given the infrastructure limitations.
Apparently, it's a big deal.
Consider, for example, an oil pipeline network represented in this figure. So you have directed arcs, and in this case the weights of the arcs describe the capacity of this arc. In particular, for our example, it would be the amount of oil that we can send per hour, say in thousands of barrels per hour. Then this means that the most we can send from node 1 to node 2 in 1 hour would be 1000 barrels. The most we can send from node 2 to node 4 in 1 hour would be 4000 barrels, and so on. We can see that there is a specially designated node here marked by S and another node marked by T in this network. So the node 1 marked by S is called the source, and the node 6 marked by T is called the sink. And our goal is to push as much oil as possible through this pipeline per hour from node 1 to node 6 or from source to sink. Mathematically, this problem can be stated as a maximum flow problem in a directed capacitated network. So we have this network G given by the set of nodes N and the set of arcs A, and we have the arc capacities that will denote by Uij's for every arc ij belonging to A. For example, U52 is given by 2. Okay, so and we want to determine the maximum possible amount of flow that we can send from source to sink so that no arc capacities are violated. For example, we could send 1 unit of flow through the path from 1 to 2 to 4 to 6. We can see that we wouldn't violate any capacity constraints along this route. And then we could send another 2 units of flow through the bottom path by going from 1 to 3 to 5 to 6. This would give us the total of 3 units of flow. But the question is this the most we can do, or maybe we can push some more of the flow? This is one of the simplest variations of the maximum flow problem. There are many others that consider all kinds of different practical considerations, but in this video we are going to focus on this simple version. Let's first develop a linear programming formulation for our problem. Our decision consists in deciding how much of the flow we are going to send through every arc, so it makes sense to define our decision variables accordingly. We'll denote by xij the flow through the arc ij, and we introduce this decision variable for every single arc in the network. And of course the flow must be at least 0 and at most the capacity of the corresponding arc. So we have xij's are all between 0 and uij. So we'll have one decision variable for every arc in the network, so there are as many decision variables as there are arcs, and this number would be 9 for our example. Let's think about what type of constraints we need to introduce. So for the flow to be feasible, we need to make sure that all the flow comes out of the source, then nothing remains in any of the intermediate nodes, and all the flow arrives in the node T. Therefore, for the intermediate nodes, we can write down what we call the conservation of flow constraints. We need to make sure that the amount of flow that comes into every intermediate node is exactly the same as the amount of flow that leaves the intermediate node. So the conservation of flow constraints should hold for all the intermediate nodes, but what about the source and sink? So as we said, for source we have only outflow, we don't receive anything at node S, and for T the balance of flow is supposed to be positive because we receive and we don't send. So we could introduce the decision variable for the amount of flow that comes out of node S and arrives in node T, and this amount must be the same, right? Because whatever we send from S we should receive at T. And then we could say that this amount is equal to the sum of x12 and x13, because we need to send all of this amount out of node 1. Let's denote a decision variable by f, let's say. So this is our total flow, right? So then f should be equal to x46 plus x56. Or alternatively, we could introduce this artificial arc here from the sink to the source and say, okay, this is the amount that we send from S to T, and to make this conservation of flow constraints that we have for intermediate nodes hold for both source and sink, we can artificially send all the amount that we receive at node T back to the source. And this way we will have the conservation of flow constraints satisfied for all nodes in the network, including the source and the sink, right? So this is the approach that we are going to take. So we introduce this artificial arc from the sink to the source, which is going to send all the amount received at the sink back to the source. And then we can treat this arc as a regular arc, except for we don't have the capacity for this arc, so we don't need to specify the capacity constraint. But other than that, we could write down all the same conservation of flow constraints now for both source and sink. So let's write the conservation of flow constraints for every node. So first, for node 1, we will have XTS. So this will be the amount of flow that we artificially send through the artificial arc from the sink to the source, right? But this is the same amount that we are sending out of the sink to start with. So XTS is supposed to be equal to X12 plus X13. So we send this amount out through the two outgoing arcs that we have at node 1. Then for the second node, the conservation of flow constraint will look as follows. So we receive from node 1 and then we send to nodes 3 and 4. Therefore we'll have X12 is supposed to be the same as X23 plus X24. For the third node we have 2 incoming arcs and 1 outgoing arc. So we'll have X13 plus X23 is equal to X35. Then the fourth node, we will have 2 incoming arcs and 1 outgoing arc, which gives us X24 plus X54 is equal to X46. Then for node 5 we have 1 incoming arc and 3 outgoing arcs. Therefore we'll have X35, the amount that arrives into node 5 is supposed to be equal to the amount that departs node 5, which is X52 plus X54 plus X56. And then finally for node 6 we will have 2 incoming arcs and 1 artificial outgoing arc. So we'll have X46 plus X56 is equal to XTS. Alright, so I decided to denote this XTS differently, not as X61, even though it's the same thing, right? But to make sure that we keep in mind that this is the artificial arc that we are talking about here, and this is the flow through the artificial arc. And then our objective is going to be maximize the total flow, which is given exactly by XTS, right? So this is our objective. And then of course we'll need to have the bound constraints for all the variables except for the variable XTS, and this will complete our formulation. Here we have this formulation written for the general case. We are maximizing XTS, the artificial flow we return from the sink to source, and then we have the conservation of flow constraint for every node I in the network, And you may notice here that instead of A, we are using A prime. This is because we need to take into account this artificial arc that we added. So A prime is nothing else but A with the artificial arc included. This way we can write all the conservation of flow constraints in one line instead of looking at S and T separately. And the conservation of flow constraint states that all the inflows into I are the same as the outflows for I. So this is the amount that comes into I, and this is the amount that leaves I, and these two amounts are equal or the same, their difference is equal to 0, right? And then finally we have the bound constraints or the capacity constraints for every variable except for the variable corresponding to the artificial arc. So this summarizes the LP model for our maximum flow problem.